In the last two videos, we saw some example of reciprocity laws. In the case when f was a quadratic polynomial or when f was the acyclotomic polynomial, we saw that split f can be given by a congruence condition. A natural question then is this always gonna be the case? Is it true that split f can always be given by a congruence condition? Well, unfortunately no. Or maybe it's fortunately, because that's how we get interesting theories. Anyway, it turns out that split f can be given by a congruence condition if and only if the splitting field of f is an abelian extension of Q. By this we mean that its Galois group is abelian. So where does this come from? Why is this true? Well, underlying this is some deep idea about the relationship between split f and the Galois group. This link is given by the so-called Artin map, which associates to most rational prime P an element of the Galois group of the splitting field of f over Q. It turns out then that the set of primes that f split over this split f is just gonna be, roughly speaking, the kernel of the Artin map. That is gonna be true for all but finitely many rational primes P. So that's the story we're gonna discuss in these videos. Let us start though by proving one direction of this abelian polynomial theorem. Let us show that if split f can be given by a congruence condition, then the splitting field of f is gonna be abelian over Q. Now here, by split f can be given by a congruence condition, we mean a very specific thing. If you want to see a more general treatment of this, you can look at our survey video on class field theory. For now, let's say that this means that split f contains the following set. Let us assume that to say that split f can be given by a congruence condition means the same thing as split f contains a set of all primes congruent to 1 mod A, where A will be some product of primes, rational primes, ramifying in the splitting field of f. What is significant about the primes that are congruent to 1 mod A is that from our previous discussion, we know that these are exactly the primes in split of the acyclotomic polynomials. So saying that split f contains all the prime congruent to 1 mod A is the same as saying that split f contains split of the acyclotomic polynomial. And now here is the interesting thing that we have mentioned in the overview. Remember that split f actually uniquely determines the splitting field of f. To be more precise, we'll have that split f contains all but finitely many points of split G if and only if the splitting field of f is contained inside the splitting field of G. Thus now coming back to our discussion, if split f is given by a congruence condition, i.e. if it contains split of the acyclotomic polynomial for some A, then the splitting field of f must lie inside the splitting field of the cyclotomic polynomial, which is just the cyclotomic field. And so since the cyclotomic extension of Q is abelian, Q of f itself must be abelian over Q. Thus one direction of this abelian polynomial theorem just follow from the fact that the set of primes that f split over uniquely determine the splitting field of f. So let us give an idea of why that might be the case. Underlying this proof is another theme of class field theory, namely the density theorems. We can define a notion of density of primes, and then we'll see that split f is completely determined by the degree of the splitting field of f over Q. This will then show us that split f must uniquely determine Q of f in the following way. Previously, we were talking about only split primes of a polynomial. Now we want to talk about split primes of an extension of Q. And these are not always going to be the same thing. So let us quickly the definition of what it means for a rational prime P to split in a number field K. Let's say K is an extension of Q of degree n. Then a rational prime P is said to split completely in K if its extension in OK factor into a product of n distinct prime ideals, where again n here is the degree of this extension. And we'll denote the set of primes that split over K by SPLK, and we'll call this split K. Now, it's not always going to be the case that split QF is going to be equal to split F. To learn about the relationship between these two sets, you can look at our video on splitting up primes in Dedekind domain. But for now, for convenience, let us just assume that they are basically the same thing. And actually, the weak Chebotarev theorem applies for the set of split primes of an extension. That is, the density of the set of primes that split over an extension of Q is gonna be equal to the reciprocal of the degree of the extension. So now, coming back to our theorem, let us see why then split F should determine this extension, Q of F. One direction of this is not going to be hard to see if you understand the definition, so let's look at this direction. Let us suppose that all but finitely many primes in split G is contained inside split F. Let us see now why that would imply that Q of F must lie inside Q of G. To that end, let us form a compositum L of this QF with QG. Then it's not hard to see that split L must be the intersection between this split of QF and split of QG. Now recall that because we are lazy, we have assumed that this set of primes that split over QF is just going to be equal to split F. So we must have that split of QG is contained inside split of QF by this hypothesis, and thus this intersection is just going to be split of QG, with up to finitely many exceptions. Now we need to relate this relationship back to the extension QG and QF, right? And as we've mentioned, a way to do so is via the Chebotarev density theorem. We can take density on both sides, and thus this gives us that the degree of L over Q must be equal to the degree of QG over Q. In particular, this means that QG must be equal to L. Thus, Q of F must be contained inside Q of G. And therefore, we see that split F uniquely determines the splitting field of F. The reason underlying this being that the density of split F determines the degree of this extension. So coming up next, we're gonna briefly discuss these density theorems, after which we'll define the Artin map and come back to finish the proof of the Abelian polynomial theorem.